So now, when we look at this one, please. Okay, so on the spill, let's start with the spill. What happens in a spill? So for the spill, what I need you to note is that, remember we have motor and we also have what? Generator. Generators. Okay? Right. So in motor, this one, it gives what? It gives the current. The current gets movement. So you can definitely apply the right hand rule in motor, and then in generator it gives movement, then it gets the current. So everything will make sense. Let's just keep moving, don't worry. And then we can also use the right hand rule in generator. Okay, so this is what happens in the spill. What about the external circuit? So let me quickly write down the external circuit here. Okay, so this one on the external circuit, it's very important that you understand how the current direction work. Okay, so on the external circuit, it's all about the current direction. That's what we're going to look at now. So remember, we're going to have motor and generator, and then let's say this is for motor and generator. And then we're going to have only generator. Right. So if we look at this, how do we know if this thing is how do we know if this is a motor or a generator? We're going to see this by a split ring. And how do we see that it's only a generator? You're going to see by the slip rings. Are you still with me on that?
Yes, I am.
100%. Okay, so now remember we talked about the palm. Remember when we were doing the right hand rule? I'm not sure if we still have this information on this. Yes, I think we do. Remember we talked about the palm of your hand. This part here, we said it gives us, it's either the direction of the force or the direction of the current. Okay, so you'll see when we work on this one, don't worry. Okay, so now if we go back down, let's go back down and complete this one. So in motors and generator, what you need to note is that the current in a loop. So the current in a loop, it's always what? It's always in the same direction. It's always in the same direction. Right. It's always in the same direction at the same pole. Why is this the case? Because the spill turns in the same direction. You understand?
Sorry, what do you mean by spill?
Please come again.
What do you mean by spill?
Okay. I'll show you this when. Let me just when we do a past paper maybe.
Okay.
Okay. When we do a past paper, I'll just show you the a picture what we mean. What is a spill? Okay.
Okay.
Okay. Okay, just give me a second. Okay, thanks. Okay, so now let's go back to what we're currently working on. So now when we look at this one, for this one, we said that on generator, the current direction, the current direction in the loop, what will happen to the current direction? It will remain the same. It will remain the same. It will remain, let's say, same direction. Okay, it will remain same direction at the same pole. So the current between motor and generator, the current will always in the same direction at the same pole, and then same when it is on only generator, the current direction in the loop will remain in the same direction as the same pole. Okay, so now for this one, for motors and generator, this one is the same direction in the external current, and then in only generator, it's alternating direction in the external current. Okay, so meaning this side is going to the current move over the split. It cannot move over the split. So let me write this down. The same direction in the external circuit. So meaning that the current in motors and generator cannot do what? It cannot move over a split. This side, we say it's in alternating direction. It will move in an alternating direction in the external circuit. Okay, so now the current, it will move over a solid ring. This side, the current, it moves over a solid ring. Okay, and that's it for this one. That's it for this one. I just want us to talk about the current size in motors and also in generator so that we can do some of the calculations, okay?
Okay.
Can I move down?
Yes.
Okay. So now I want us to discuss the current size, the size of the current. Okay, so on the current size, just know that when it comes to motors, it remains the same. It remains the same. That gives what? That gives direction with the battery. That gives direct current with battery. So nothing will change. The size of the current will be the same. Okay, so now in generator, when we talk about generators, in generator, it's going to change. The current, it's where the current change. So generators, the changes, the entire time. So the current will change the entire time. Okay, so the reason for this is because it is induced by the turning loop. By turning the loop. Okay, let's go into details. So let's say I have a north pole and a south pole here. Let's say I have a north pole and a south pole. So now, when you look at this, let's say that we have the field lines. These are your field lines between the north and the south pole. Are you still with me?
Yeah.
So on these field lines, if the movement direction of the loop is perpendicular on the field lines, so if it's perpendicular, it will be like this.
Yeah.
So that's how we say it's perpendicular, right? So if the movement direction, if the movement direction of the loop is perpendicular on the field lines, the size of the current, we're gonna say for this one, the size of the current is maximum. You understand?
Yeah.
100%. But now let's say that the movement direction, let's say this is my north pole, this is my south pole. So these are the magnetic lines. So let's say the movement, you see the arrow where the arrow is pointing. The movement is in the same direction as the, let's say it is, let's say this thing, they are moving in that from north to south, north to south. So if they're like that, we can say that they are moving in the same direction. If they are moving in the same direction, the movement direction of the loop, it's in the same direction as the field lines, the current will be zero. You understand?
Yeah.
You sure?
Yes.
100%. Okay, so now when it comes to the current, sometimes we can also look at if this is a direct current generator or if it's an alternating current generator. Okay, so now let's say this thing is an the direct, we're gonna do for direct current generator. So for direct current generator, we set this guy, we see this by split ring. And then, so for this one, the current direction, it will remains the same. Okay, but what will change? But the size changes. You understand?
Yeah.
Okay, so I need you to note down all these notes. You're going to see how we're going to use this note to answer exam questions. So now, for alternating current, so for alternating current generator, this guy, we're gonna see it by slip rings. So for this one, for alternating current generator, we say that the current direction and the current size is gonna change the entire time. That's the difference. Okay, are you happy with that?
Yes.
Okay, so now for alternating current, we use alternating current generators at power station to generate current, you know?
Yeah.
Okay, so this guy here, they will ask you where is the AC. They'll ask you where is this AC used. So the AC, it is used at power stations. They'll definitely ask you this one. If you don't get it now in prelims, you might get it in your final exam. At power stations, and then, or they'll say, what is AC used for at power station? You'll say to generate current. So please trust me, when it comes to electrodynamics, this has too much, like it has to do with theory and less calculations. Okay, so
Yeah.
what is the reason that the AC are used? What is the reason that the AC are used at power station? uh, Reason is that they must be transported over a long distance. Small current and large potential difference to lose as little possible energy. When we say little possible energy, we are referring to high voltage wires. And also, remember, transformers only work with alternating current. I'm just going to give you reason, the easiest reason why AC are used at power station. The reason is that transformers only work with alternating alternating current. Are you following?
Yes.
Okay, so you will be required to calculate the value of the current and voltage. So this is where you will be required to do some of the calculations. Now, you'll be required to do the value of current and voltage. So I need you to be ready with handwrite rules because we're just gonna do a short past paper. Né?
Yeah.
Okay, so now the size of the current and the voltage, they change the entire time and must therefore use the average values. For example, so uh, for the voltage is gonna be, I'm not sure if they say V average, but we'll confirm that when we use past paper, V max over root 2, and then for the average current is gonna be I max over root 2. And that's it for this one. That's it for this one. So remember, before we move to past papers, there's something that I need you to note. If you still remember now, what you're going to do, Ohm's law and the first equation can also be used in alternating currents. So in alternating circuits, for example, remember Ohm's law says R is equals to V over I. That's Ohm's law. So this, when we work within electrodynamics, we can write it like this. R is equals to the V average, which is this one, the one that you calculated. You divide that by the I, what? The I average. We'll confirm if it's average, né? If we say
Yeah.
average. And then same applies. The power, which is also part of Ohm's law, V over I, we can write this as the V average times the I average. So those are the formulas that we can use and so forth. It also I squared times R. You can also do for V squared over R. You understand?
Yes.
Okay, just give me a second. Let me open a past paper, okay?
Okay.
This is about time where you see why I said that this is all about you understanding the theory, you understand?
Yeah.
Okay, let's look at this. This is question 9. The diagram illustrates two devices X and Y that operate in oppositely to one another. Okay, X and Y, device X, and this is device Y. So now you can see these two devices, and now we're just gonna try and answer the following questions. Ne?
Mm-hmm.
Okay, let's start with the first question. Okay, let's see. Okay, the first question, 9.1.1. Identify between two devices, which one is an AC generator. I'm not sure if you still remember the notes that I gave you. Do you want me to go back up? Let's go back this side first. Ne?
And okay.
Okay, so if you still remember, I gave you some of the notes here, and you see this table. This table is very important. This table is
Yeah.
the one that can help you to differentiate between DC motor, AC motor. You just have to look at the split ring or the slip rings. So if you look at this one, if you look at this guy, we said that DC motor, where is it? Okay, we talked about DC motor. We said DC motor, they have one split ring commutator with carbon brushes, and then AC, they have two slip rings. And then for DC generator is one split ring. And if you look at this question, let's look at this one. Because of this gap here, because of the gap, this commutator, we're gonna call it, this is the slip ring. Do you understand? I'm
Yeah.
sorry. It's a not slip, but it's a split because it is into two parts. You understand?
Mm-hmm.
I'm sorry about that. So this will be split ring. And then this one are, what's going on here? Why did they write slip rings? Because that's not, oh yes, that's slip rings. So this one are slip rings. Okay, so now we know which one has slip rings with carbon brushes. Then that's when you can use the table to understand which one is an AC. So by looking at device X, we can see that device X is the one that is is the one that is an AC generator. Do you understand?
Yeah.
Okay, so if we go to this part, we said that AC generator, they will have two slip rings with carbon brushes. Two slip rings with carbon brushes. And if you look at this, we have two of them. We have one and then we have two. So there are two of them and both of them, they have brushes. This makes device X to be an AC. Do you understand?
Mm-hmm. Yes.
Are you still with me?
Yes, I am.
Amy, I'm showing you how to be the best. Né? If you can understand
Yeah.
that table, you are good to go. Look at this. State the energy conversion that occurs on device Y. So first thing first, what is device Y?
Device Y is a DC motor.
Device Y, because it has a split ring, it only has a split ring with carbon brushes. So it's going to be a DC motor, not a DC generator, okay?
Yeah.
How do we see the carbon brushes? You're gonna see the carbon brushes. Sometimes they might not give you the name of carbon brushes, but just look at if your split rings are connected to something there, those are carbon brushes. So this makes it to be a DC motor. So since it's a DC motor, they need the energy conversions. You're going to use your diagram. So the energy conversions for DC motor, what is the energy conversion? Is just from electric energy to mechanical energy. Can you see what we were doing on previous lesson?
Yes.
Amy,
Wait, sorry, how do you differentiate between AC generator and DC generator?
how do we?
Differentiate between AC generator and DC generator?
Oh, okay, nice. That's a very nice question. Now look at this. Look at this. Now you just have to look
Mm-hmm.
at the split it's for DC, and then sleep
Okay.
is for AC. But look at this. Between DC generator and DC motor, both of them, they have split. But in DC motor, the split is connected to carbon brushes, but in DC generator, it's just a split ring only, no carbon brushes. That's how
Okay.
you see the difference there.
Mm-hmm.
So
Thank you.
the first question, they say identify between these two, which one is an AC. So we looked at the split rings. This one has 2 slip rings. Then you look at the table, which one has 2 slip rings according to your table. 2 slip rings, it's an AC generator, you understand?
Yes.
Right, because the 2 slip ring, that's your AC generator. That's how we got that one. Then we know that device Y is going to be a DC motor, not a DC generator. It's a DC motor. Why? Because it has a split ring that is connected to carbon brushes. And then since it's a DC motor, what is the energy conversion? You use that table. It's electrical energy to mechanical energy. Are you happy with that answer?
I am, yes.
Okay, so the energy conversion, that's electrical energy to what? To mechanical energy. I'm sorry about the spelling there. It's mechanical. Right.
Yeah.
Come on, Amy. You can see what we were doing. You know, sometimes when we do the notes, uh, you'll be asking yourself, why are we going so much trouble? Why are we doing this lot of notes? What is the aim? Look at the next question. Name the principle on which the generator operates. And I think I did give you the principle. Did I give you the principle?
I don't remember.
I did.
Oh, okay. Sorry.
You need to go through the notes. They will help you. Trust me. The principle for motor, the principle for this one, for DC motor. You see, the principle for DC motor, we said, is gonna be motor effect, and then the principle for AC generator, it's electromagnetic induction. So we said this one is the same for DC. It will also be electromagnetic induction. So meaning that this generator, it will be electromagnetic induction. So the correct answer, if they ask you about the principle, you just write electromagnetic induction if it's an AC. So let's go back to the question and understand what is the question. Say, name the principle on which the generator operates. We know that generator, we said that the generator, the AC and the DC generator, both of them, they will be under electromagnetic induction. So the answer for this one, it's electromagnetic induction. Are you following?
Yes.
Okay. Name one structural difference. Oh, listen, when they say name one structural difference between the two devices, you just have to tell them that X has slip rings, Y have split rings, then you are done. Or you can tell them about the
Okay.
load or the power source. But for now, I just want you to focus on this easy one, slip rings and split ring. You're just gonna, when they say name one difference, so you're going to say for X, we have slip rings, and then for Y, we have split ring commutator. I'm not sure if you understand that. Just to understand the nodes, you are good to go. Okay. I think we talked about this question yesterday. And I'm not sure if it's yesterday or a day before yesterday. To answer this 9.1.5, write down one way to improve the efficiency of device X. Device X, we said, is an AC generator. And I'm not sure if I did give you this notes. Let me just quickly confirm and see if I gave you everything. Okay, I don't see this one, but in order for us to improve the efficiency of AC generators, is that we need to use. Maybe if I say this, you'll remember something there. Use use of strong magnets. Did I mention something about magnets on our previous
Uh,
lesson?
I don't think so.
Okay, we need to use stronger magnets, or we can definitely increase the number of coils. Maybe for sure tomorrow I'll do a practical with you so that I can show you how this works, how this rotates. Don't worry, maybe tomorrow I'll do it with you.
Sorry, could you also say to move the coil faster or no?
Can I?
Could you also answer this question and say to like move it faster? Or is
Uh,
that not right?
I'm not sure about that, but I can definitely confirm that for you, okay?
Okay, thank
Right.
you.
So from this question, there are other questions here that we need to answer. I'm not sure if they are on. Okay, they are not here, but I think I definitely need to add them on this remaining 5 minutes. It will be very fast. It has to do with calculations. This will take 5 minutes of your time. Let me. Okay. I just want to add one more question. Why it keeps on doing this? Okay, so we're done with this part. Let's answer the following questions. So on
Yeah.
this one, I'm just gonna look at what we are given on this 9 point. This is 9.2. Wait. Oh, I think I did tell you that it's going to be average.
Yes.
Can you read the question? It says determine the average power. So yeah, we use average. That one is confirmed. So let's look at this. They say an AC source in a circuit delivers an alternating voltage. Okay, we can just look at this diagram and answer the following question for 9.2.1. Determine the peak voltage. So it's like they are looking for the Vmax. Okay,
Yeah.
they are looking for the Vmax. Let me just quickly write this down. So when they look for the Vmax, unfortunately, we don't have much time, but I'll show you. Let me work on this 9.2 this 9.2 only, then I'll show you on our upcoming lesson what you need to do, how to choose the correct formula. So you'll find the formulas. You're going to look the formula that has the peak voltage. So the peak voltage is the Vmax. You're gonna look for the formula that has Vmax, and I think I did give you the formula today and say V RMS it's equals to Vmax. Oh, it's RMX over the root 2. Okay, so we are looking for Vmax, and the VRMS is given as 20. So we can just substitute this and say this is 20. This is equal to Vmax over the root 2. Make Vmax subject of the formula, multiply both sides by the root 2, which gives us Vmax to be equals to 20 times root 2. Then you punch that on the calculator. The answer that you get is your peak voltage. So tomorrow, I think we can just work on, I'm not sure if you're available in the morning.
I am, yeah.
Because if you are available in the morning, this gives us an opportunity to do 2 sessions during the day
Okay.
and also at 5. You understand?
Okay, that's perfect.
Yeah,
Just let me
so
know what time.
I'm listening.
I said you can just let me know anytime.
Yeah, no, it has to be 12. Tomorrow 12, ne?
Tomorrow at 12, okay.
Yeah,
That's good.
tomorrow 12.
Alrighty, thank you so much.
Yeah, thanks. We'll continue with calculations, okay? And we'll do more of the past papers. Just go and read the notes that I gave you. Can you see today why those notes are very important?
Yeah.
And all those notes, they help you answer all these questions. Can you see that?
Yes, I can.
Okay, sharp, sharp. Have a
Okay, thank you
great
so much.
evening.
Have a good